Hi, I'm Ali from National University of Singapore. I'm going to present Levioso, a comprehensive and efficient mitigation for speculative execution attacks. This work is done in collaboration with Archid Agarwal from UC San Diego, Andreas Diavassos and Teber Carlson from National University of Singapore. In 2018, a new class of attacks was introduced called as a Spectre, which affects almost all modern CPUs. This attack exploits the main performance enabler feature of these CPUs, and that is the speculative execution. As mentioned by John L. Hennessy in his Turing Award lecture, this attack shows a sorry state of security in computer architecture. In the next two slides, I will present two main examples of leakages through Spectre-type attacks. The first example targets sandbox code. As you can see, in this code, the victim performs an array bounds check before accessing the array A, and the expected behavior is that the array A is accessed only if the index is within the array bounds. However, an attacker can force the CPU to mispredict the branch which is handling the array bounds check and potentially access an arbitrary memory location which can potentially be a secret. In the second example, we show the vulnerability of constant-time cryptographic programs. In these programs, the secret is loaded non-speculatively but never leaked before they are legally declassified. For example, in the shown program, the state is secret at the beginning and it is allowed to leak only if all rounds of decryption are completed. However, the for loop can be skipped due to branch misprediction and leak the secret state before it is legally declassified. To mitigate speculative execution attacks, most of current hardware-only solutions restrict execution of all instructions that can possibly leak data mis-speculatively. For example, you see two example code snippets of sandbox and constant-time programs. Hardware-only defenses restrict execution for all instructions after branches until the correct path is resolved. These solutions can be very expensive in cases that branches take a long time to resolve. So we ask this question, is there a solution to provide a more selective approach and allow execution for the instructions that are guaranteed to be safe? In this work, our key insight is that a static compiler analysis can determine the instructions after a conditional branch that will leak the same data even if there is a misspeculation. In other words, they are independent from the outcome of unresolved branches. Here you see the same snippet for sandbox code, and in this code the value of x can be different based on the branch outcome and it's vulnerable to a Spectre. So we need to restrict their execution. However, the value of y is the same independently from the path executed after the branch. Hence, it is safe to leak the value of y even if the branch is unresolved. In the next example, you see the snippet of a constant-time code. Here we need to restrict the loop body as it directly depends on the branch outcome. And also we need to restrict the leakage of state 1 since its content will be different based on the control-dependent instructions. However, the contents of state 2 is independent of the loop branch and it will leak the same values. Hence, there is no need to restrict its execution even if the loop branch is unresolved. Based on these key insights, we propose hardware-software co-design that first uses a static compiler analysis to detect true branch dependencies and then communicate this information with the hardware in order to apply restrictions only if necessary. Levioso's compiler consists of 3 steps to detect the true dependence of each conditional branch. First, we detect the control dependence, and this includes all the instructions that can possibly execute between the branch and its reconvergence point. Note that the branch reconvergence point is the point in the program that the control will eventually reach regardless of the branch outcome. In this example, the reconvergence point of the branch in basic block 1 is basic block 4, and all instructions in basic block 2 and basic block 3 are considered as control dependent. In the second step, we detect the data-dependent instructions, which includes all the instructions after the reconvergence point, where their input data can be different based on the path executed after the branch. In this example, we have marked the instructions in basic block 4 that are data-dependent. Finally, we embed this dependency information through x86 prefix bytes of the instructions. We inform the hardware if the instruction is analyzed by our compiler alongside of a branch ID for the branch instructions and the most recent branch of the branch that each instruction depends on. Once the branch dependencies are detected and embedded in the code, the hardware extracts this information when decoding instructions. If the instruction is a branch, we add a table called unresolved branches table where it keeps track of live unresolved branches. For all decoded instructions, we set them as restricted when inserted to the ROB if they depend on an unresolved branch in the UBT based on the compiler information. Finally, once a branch is resolved, we leave restrictions for its dependent instructions. In this slide, we show an example which demonstrates how Levioso shows better performance compared to prior work. For example, in this example, we use Dolma. In this example, we have two branches, BR10 and BR11, where Levioso had marked which instructions are dependent on each of them. Also, note that BR10 is a long latency branch since its condition depends on the load that misses in the cache. Since Dolma doesn't have compiler level information, it restricts execution for all instructions after the branch BR10 until the branch resolves. However, Levioso only restricts execution for the instructions that are truly dependent on BR10, which in this example are only 3 instructions. This means the independent instructions are allowed to execute and potentially improve memory level parallelism for the subsequent long latency memory accesses if they are independent from the unresolved branches. And in this example, that last load in the code is such a long latency load that we discussed, and that load will be issued earlier in Levioso compared to Dolma. We implement Levioso in Gen 5 and use a golden code-like microarchitecture for simulation. We simulate a subset of C and C++ applications from SPEC CPU 2006. Also, we have implemented Levioso's compiler in LLVM, and you can find the link to our open source GitHub repo in the paper. In our simulation, we compared Levioso with 2 prior hardware-only mitigations with the same protection scope as Levioso, covering both sandbox and constant time leakages. Our results show that Levioso incurs just 23% performance overhead compared to 51% overhead of Dolma and 43% overhead of STT, which means we can reduce the overhead of prior defenses by almost 2 times. To conclude this presentation, we presented Levioso as a hardware-software code design that provides a comprehensive protection for both sandbox and constant-time threat models. Also, Levioso significantly improves the performance compared to hardware-only defenses, since it only applies restrictions if necessary and informed by the compiler.